Obrigado.
Okay, so my plan for today is talk about the maximum principle and some consequence of it, like uniqueness, but also many other consequences. The maximum principle is one of the main tools that has been used so far in the subject. And the first thing that I want to talk about is that I will be using all the time is the following lemma that is due to Hamilton. So suppose that you have a function that depends on two parameters, x and t. That is C1 in time. Then the function u max of t, that is the, so, okay. In some k, let's say, of u of xt. Here I should have defined where this is defined, so I'm going to say that this is k cross 0t on R, let's say. And k is compact. This is compact. So this function is Lipschitz. And du max dt at t is the same thing as du dt x naught t, where okay. So I'm going to be using this all the time, and of course you can replace the maximum here by the minimum. So I'm going to use the equation, some equations that this satisfies to find equations for this quantity here. Let me give you an idea of the proof. It's a very simple proof. And the idea is that you can write u of xt as, okay. So I'm going to use a Taylor expansion here. Let me see in which order I wanna do that. I think it doesn't matter because I want to do it both ways. You can write this ut plus epsilon as ux of t plus du dt next c times epsilon let's say. This is actually open. It doesn't matter. But then what you can say is that if this is bounded, then u of x t plus epsilon this is equal then u of x t plus epsilon times some constant, and this is by definition less than the u max of t plus epsilon times c. So now I can choose the x in a way that this is exactly equal to the max. So here we choose x. As it's not. So this is So basically what you can see here is that u max t plus epsilon max of t divided by epsilon is bounded. So this way you can see that the function is Lipschitz, and actually if I hadn't replaced this by its bound, you can actually see that this is actually converging to the derivative at this point because of the way I chose that. So similarly, you see that du max dt at t and you can play the same trick the other way around. You can, instead of replacing this here, I can bound this one by u max. And try to choose the x in a way that the maximum is attained on this side. And then I would get the opposite inequality. So also repeating this. We get that du dt max is actually bigger than dut, and that's all we need. Anyway. So I'm going to be using this all the time, sometimes with the maximum and sometimes with the minimum. You will see how I'm going to use it in the next theorem. So what I want to say, maybe I don't want to write it maybe in all the generality that I wrote it in the notes, but you can see. So, okay. What I'm going to say here is true actually not only for mean curvature flow, but any reasonable geometric flow. And I guess there was a line here already. So let me move. Maximum principle. Oops, sorry. Let me turn this off. So assume that you have a family of Riemannian metrics. And that U satisfies something like this. Plus U, gradient of U, you can have here T also, and gradient of U. Here I wrote it this way, but it doesn't really matter too much. I mean, that this is terms that have the gradient of U somehow. B of U. Then U T maximum is less or equal than B of U. And in particular, Umax. In particular, if the HDT then max so this is a very general statement, and actually it's true for any geometric flow that has a smooth metric. In my case, g of t is going to be the metric induced by the mean curvature flow, but this could be the metric in the Ricci flow or in any other geometric flow. And the proof is actually direct from this fact here, from this lemma here, because at the maximum, we know that this term here has a sign and this term here is 0. So this is direct from that there. Direct from the lemma. And you can say the same thing about the minimum if you have the opposite inequality here. And this is a very simple theorem in some sense, but it has a lot of very important consequences, as I'm going to try to explain today. So, okay. So let me write one more theorem on this direction. There is that sort of uses, it has the same flavor as this here, that will be the key to prove the uniqueness that I promised yesterday. So suppose that I have two evolutions. F1 are solutions to mean curvature flow. And I'm not going to say anything yet because I'm going to write that in the corollary maybe. Then the distance between F1 and F2 is an increasing function of time, or not decreasing, I guess is the correct. Assume that let me say a little bit about what I'm assuming here. There are assumptions that are important here. As I said yesterday, F1 and F2 have codimension 1. This is not true for higher codimension, or at least it's not as simple. And I will assume that they are not intersecting at time 0. You can say something when they intersect, but I'm not going to talk about that. Time 0. This is time 0. So this means that they're not intersecting at the starting time. So actually, this theorem has very important corollaries, and the proof is very much related to what I said before. And so let me try to say why I'm trying to prove this, or what can I say by proving this. So what I'm saying here is that if you start with some surface, let's say F1, and a different surface, F0, or F2, sorry, then the distance between these two things, I don't know if the distance between these two things, the minimum distance, that's maybe here, is going to be increasing in time. So these two things are never going to touch as long as I have an evolution. So in particular, this is increasing. So the first corollary is that, in fact, I have uniqueness. I cannot have two different evolutions of this thing. I cannot have two different evolutions coming out of the same initial condition. So how can you see this? Take your two evolutions and let one evolve a little bit. So let it move out a little bit. And then compare these two things, and these two will never touch, but in the limit they should be exactly the same thing. So actually this tells you that you have a unique solution. Corollary important. Second corollary that is important, and this is true only in the case of codimension 1, it's not true if you have higher codimension. You will see from the proof that, in fact, this tells you that not only the distance increase, but a surface cannot touch itself during the evolution. So this also tells you that if the initial condition is embedded, then it remains embedded for all times. You will see it from the proof. And the last corollary that I want to discuss of this particular theorem here is that okay, so yesterday we computed an example that is the evolution of a sphere, and that was converging to a point in finite time. So what this tells me is that if I have something compact, I can put this inside a sphere. So in particular, that means that this can exist at most for the time that is at most for the time that the sphere that contains it exists. So exists for finite time. Another way of phrasing this is that the solution has to develop a singularity in finite time. So my lecture tomorrow is going to be about what do I know about this singular time. Today, what I want to do is, well, prove this theorem here, and then use the maximum principle in different ways to tell you how smooth is the solution while it exists, and what can I say about the singularity formation just from the comparison principle, or at least a little bit of that. So let me talk about the proof here. So let's take the points where the minimum distance is attained. I'm assuming that everything is compact. If things are not compact, as I said yesterday, you need to work a bit more to do these things. But suppose that between F1 and F2 is attained at P1, P2, respectively. If the distance is attained at these 2 points, that means that the tangent planes at those points are parallel. That's just because of the minimality. So what I'm going to do here at this, so I have basically the same plane, and what I can do then is near these points, I can write my surface as a graph over the tangent plane, just around that point. And because it's the same plane, I can basically write the solutions as a graph over the same plane near the points where I find, where I attain the distance. So we're going to write okay, so this means that I can write that this is the graph of a function, so I can write this as, so without loss of generality, I'll assume that the plane is basically, you know, like Rn. Assume that Fi of xt, basically. And just because I have to choose some order, I'll assume that f of, that the distance is attained at 0. F1 and F2. That this is positive. So I'm assuming that F2 is bigger than F1. It doesn't matter which one you assume. Okay, so what I'm gonna try to do, what I want to do then, is try to show that the time derivative of this is positive. This is what I'm trying to do. Okay, so let's try to see the equation that f satisfies. Capital F, I guess, is a solution to character flow. We can compute, I'm not going to do it in detail, but it's an easy computation, that the f dt is actually the Laplacian of f, the regular Laplacian on Rn, plus some term that depends on the second derivative and on the gradient. Okay, and this is fine. Okay, so what do I want to say here? Check that I have the equation with the correct sign. I think that might be a minus. Yeah. Okay. Perfect. Okay, so let me use this to compute what the derivative of the distance is. So I'm going to call this the distance function, and I'm going to call it d of t, just not to have to write distance every time. So I'm just going to write d of t. Maybe it's not a very good choice, actually, come to think of it. Okay, so from this equation here, I have that this is the same as the Laplacian of f2 minus f1 minus the 2 of f1, gradient of f1, the other way around, because the 2 is the plus d2 of f1, f1, f1. Okay, so I'm taking all this at x equals 0. And notice the following, because this is the point where the distance is attained, the x equals 0 is a minimum for f2 minus f1. Attained at x equals 0, then it's a minimum for f2 minus f1. And that means that, in particular, the gradient of f1 at 0t is equal to the gradient of f2 at 0t, and that the second derivatives of f2 minus f1 are actually negative, positive. It's a minimum, sorry, so it's positive. So okay, so basically all these things here are the same at this point. So I can take all this to be gradient of F1 if I want. And you can see that this actually has a sign. This is probably hopefully the correct sign, and this is actually positive. So what this tells you is actually that dt, very bad choice, is actually something that is positive. This term here, maybe you want to rewrite it a little bit to see that. So this term here, maybe you want to rewrite a little bit. But if you rewrite it, what you see is that this is d2 of f2. Remember that all these things are the same, minus f1, divided by this gradient that is exactly the same. Let's say f1, for instance. Maybe I don't want to do it like that. Times, yeah. Let's see if I'm trying to think what would be a good notation for this. But this is di of f1 and dj of f1. This is not a very good notation, so let me write it like this, maybe. And then if you rewrite the whole thing, what you're seeing here is that t is equal to d2 ij f2 minus f1 ei ej minus fi fj. Not good notation, sorry. The f1 dj f. So, yeah, I don't know if this is enough to convince you that this is actually something that is positive. But if not, you can go on and try to see that the fact that this is a positive matrix means that this is positive. Any questions so far? Yeah.
How do you know that the point where the distance is attained doesn't move?
It does move. That's why it has a time dependence. But I'm choosing it. So for a short time, you can assume that it's on the same, like it's something that is continuous on time because of my first lemma. So I'm fixing a time, like I'm fixing a time, and I'm just looking around that time, and this is a time where this is differentiable. Okay? So I'm just looking at this close to one fixed time. You may have to move for a different fixed time to another 2 points. No? Yes? And this is just at one time, right? At one fixed time, this you have that this is attained at these 2 points, and near that you can write as a graph. Right?
You assert that the gradients coincide for all time.
Near that particular time. Right? It's a local minimum near that time. Right? You can do this locally near one particular time.
So minimum in x and t, not just t.
Yes, but just near one, yeah. You fix t, and then near is a minimum in x t for an interval, for a short interval. Yeah. Okay, and using sort of the same proof, you can see that you can do exactly the same to look at self-intersections. I mean, if you had that these f1 and f2 were just 2 points on the same surface that were close I mean, that were to touch at some time t0, you can do exactly the same proof. And that's why embeddedness is preserved. Okay. So okay, that's what I have to say about existence. And let me see if what much I can say from the maximum principle now for other things. So other uses of the maximum principle. And I'm going to copy something here. So something that you can compute directly, and I don't think I have time to compute here, but it's a very standard computation, is the following. So since my surface is evolving, all my geometric quantities are evolving, and I want to compute how they evolve. And then I'm just going to write it down. This is something that you can compute directly, but you get that this is Hij. In general here, if you have a different flow, a different extrinsic flow, what you're going to get here is the speed. This is something that depends on the speed, and this is something that you can compute. J. Maybe I should not write all of them, but the ones that I'm going to use. Square. I think I haven't defined that, so maybe I should define that in a minute. You can also compute. This is a gradient on MT. I'm missing something, I guess. Ah, yeah. Important one. And one that I'm not going to use much, but I'm going to write anyway, so you know that it can be computed. Okay, so let me define that. So I think this this quantity was defined yesterday, maybe on the first lecture. This is the trace of the square of the second fundamental form. So this is actually the sum of the squares of the principal curvatures. So here, a squared is the sum of lambda 1 squared plus lambda n squared, where lambda I are the principal curvatures. So H is actually lambda 1 plus lambda n. And you can compute this directly in terms of the second fundamental form, but I'm not going to do it. I mean, you can write it explicitly in terms of the HIJs and the GIJs. But I think I don't have time to actually. And until what time do I have? Anyone knows? Because we started late, so I'm kind of a bit lost. It started 9:10? Okay. Okay, so I may have time to say some things. Okay, so these are equations of the geometric quantities. That is something standard that you do in the case of geometric flows. You can compute it, and of course it depends on the geometric flow. But what is interesting here is if you look at the equations, this one, and this one at least look something alike to the thing that I wrote for the maximum principle. So I can try to use maximum principle for those. Okay, so let me remember what I was planning to prove here. So, okay, so let me tell you some consequences of this. So one thing that you can do is actually, if you look at this equation here and this equation here, you can see that they have somewhat the same structure. So one corollary, if you want, of the maximum principle here is the following. If there is an alpha such that then this is preserved for all times. The idea of the proof is simple. It's just because I computed already the things there, I can compute the equation for the difference of these two things. So the proof is just compute the equation for alpha h minus a and use maximum principle. So in the notes, the computation is done. I can tell you exactly what you get. see what are the other terms, the remaining terms. Plus a squared times smarter here, and I replace this by an f. And actually, it's possible to show that this has a sign, that this is always negative. So this is less or equal than, let me call this f so I don't have to write it every time. So less or equal than delta g of t of f minus a squared times f, or plus a squared times f. So what the maximum principle is going to tell you is that this quantity is actually always positive. You have to use it for the minimum instead of the maximum. Probably I should have wrote it the other way around. Or maybe I did write it the other way around. Let me see. Yeah, I think this is this equation that I'm writing here is for minus f. So I'm writing this here. And this is like this. Sorry, there's a sign there that is mistaken. So what this tells you is that, so maximum principle implies that f is actually always negative in this way. And this is for the max. So actually what you see here is that the f max is negative. So this is interesting because that means that you can control all the curvatures, all the behavior of the curvatures by the mean curvature, actually. So if you know what happens with the mean curvature, you can know what happens with everything else. So let me make a remark here. In this case, all the curvatures. All the curvatures. So I guess the natural question maybe is when do I have that inequality? When that holds, right? When I can do that? Can you see any condition that is natural to have here in this case? That you would need to have for this to happen? Can you see any condition there that is necessary for that to happen? This is a positive quantity, right? This is the square root of that, so it's something that is positive. So at least you would need, for this to hold, that h is positive, right? Yeah, is that reasonable? So if the initial surface is mean convex, has h positive, and is compact, let's say, then you would always have this. So for this to hold, it's sufficient that the surface is mean convex and compact. Moreover, you can see that in that case, just because of this computation here, I would have that h is positive for all times. So mean convexity is something that is preserved by the flow. actually, you could see that directly also from the equation that I just erased for h. But you can do that. Another computation that you can do, and I didn't write the elements to do here, is you could ask what other conditions are preserved by the flow, right? And as something that you can also prove using a similar computation, but I'm not going to do here, is that actually convexity is preserved, and all k convexities are preserved. So let me write what that means. But I'm not going to prove it. If Sk, that means lambda 1 plus lambda 2 plus lambda k is positive at the initial time, then this is preserved. In particular, if S1 is positive, that means that all the principal curvatures are positive, and that means that it's convex, and that means that convexity is preserved. Okay, so these are some consequences of the maximum principle. Let me finish by giving you something that will be useful tomorrow. So, by giving you an example that I sort of promised to do last time. Okay, so we know that we have singularities in finite time, and as I said, tomorrow I want to talk about singularities. So, what can I say at the singular time? The first thing that you can see from the proof that we did yesterday is that if you have that the surface is C2 alpha at a certain time, then I could just start again the flow and define the solution from there, right? So something has to go wrong in C2 alpha, right? There's something I forgot to say here. Anyway. So I want to convince you that at the first singular time, or if this is converging to infinity, then I can say something about the speed at what that happens. And there's something else I should have said that I will try to say it in a minute. So suppose that at the singular time, the second fundamental form is going to infinity. Then I have the following theorem. Infinity, then I have the following. Let me put a max here, just because I don't need it to go everywhere. At just one point, I want this to fail. This is b or equal than 2 times, maybe the 2 goes here. So I know if this goes to infinity, then I know that at least it has to do it at this rate. before proving that, let me make a remark on something that I erased that I should have said. If you look at, I look a little bit at the equation for A and H, and I try to compare those, but I didn't look at the higher derivatives. If you look at that, then you will see that you can use the maximum principle again to find bounds on the higher derivatives of the second fundamental form using the previous derivatives. And that means the following, that if I have that this is bounded, then I would have that all the higher derivatives are bounded. So basically what this means is that in the flow, when I have things being smooth, they're very smooth, and when they go wrong, everything can go wrong. Okay, so this is sort of the basic estimate here. Okay, so let me remind you what the equation for A was, because I shouldn't have erased it. So what I wrote before was the following, was that d of A squared dt was equal to Laplace of gt A squared plus 2A to the fourth minus so at the maximum, because of my lemma before, this just become d of A squared max dt. This is something that has a sign. This is 0, so I just get this at the maximum. So this was my maximum principle theorem. And now I can just integrate. So when I integrate this, what I get is, what do I get? So 1 over, let's see, this is the square of that. 1 over x squared. Am I getting the correct exponent here? So we're getting the wrong exponent on this. Okay, why am I getting the wrong exponent here? I'm missing a square somewhere? Where am I missing the square? Okay, so okay. Yeah, okay, yeah, you're right. I'm missing a square. Yeah, I see what you mean. So dt of 1 over A squared max. Yeah, that's correct, right? It's less or equal to than 2 with a minus sign. Yeah, that's good. Perfect. So when I integrate here between t and s, I can say that 1 over A squared max at t minus 1 over A squared max at s is 2 times s minus t. And now take the limit when s goes to t. And I get exactly what I wrote there, that A square max at t is just going to be bigger or equal than 2 times t minus t. And I think I have a square here that it's 1 square too much, I guess. Is that correct? Yeah, all the exponents are correct. Okay, so that gives me sort of a blow-up rate that is the minimum. So like the first thing that one would like to know if this is kind of optimal or not. So this is a lower bound, right? So what I'm going to discuss tomorrow is I'm going to divide the problem in 2 cases. I'm going to call a singularity type 1 if this is exactly what is happening. And I'm going to call it type 2 when this is not happening, when the speed is faster. And probably should finish now. I'm going to start tomorrow by giving you one example that you can have singularities that are worse than actually spheres or cylinders, because so far what we know is that this is converging to a point or a line or something like that. I want to say that it makes sense because I can at least show you some singularity that is worse than that.
¿Alguna